Assalamualaikum and hello to everyone. So in this video tutorial, we will look at one question for chapter 4 involving the reheat Rankine cycle under actual conditions. Okay. So we have here a steam power plant, okay, which is operating on a reheat Rankine cycle. Okay. And then the steam enters the high pressure turbine at 12.5 megapascal and 550 degrees Celsius at a rate of 7.7 kilograms per second, the mass flow rate. And it is then reheated at 2 megapascal, okay, to a temperature of 500 degrees Celsius. Steam leaves the low pressure turbine at a pressure of 10 kilopascal and 100 degrees Celsius. Heat is then removed from the steam until it becomes saturated liquid at the condenser exit. Okay, so we have here the isentropic efficiency for the high pressure turbine 85% and also the pump 90%. Okay, so sketch the TS diagram and determine number 1 the isentropic efficiency for the low pressure turbine. Okay, so isentropic efficiency for low pressure turbine. So isentropic efficiency for the turbine, low pressure turbine. And then the net power output in units kilowatt. So W, okay, dot net total. Okay. And then finally the thermal efficiency. Okay, the thermal efficiency in units percentage. Okay, so we can start with drawing the schematic diagram for the reheat Rankine cycle. Okay, so step 1 is to draw the schematic diagram. So we have the we can start with the pump, okay, and then we can have the boiler. And then we have the high pressure turbine, okay, the high pressure turbine. Okay, and then we have the low pressure turbine. And we also have the condenser. Okay, so then we connect the components. Okay, so exiting the pump, okay, entering the boiler. Okay, so this is a reheat Rankine cycle. So the first time it enters the boiler will be the Q primary. Okay. Okay, it exits the boiler to enter the high pressure turbine. Okay, where it will produce a work output for the high pressure turbine. Okay, then it exits the high pressure turbine. Okay, when it exits, it re-enters the boiler. Okay, it re-enters the boiler for the reheating process. Okay, so there will be a Q in reheat here. Okay, and then it exits the boiler again and it enters the low pressure turbine. Okay, so here's the low pressure turbine. So it will produce a work output, and then it exits the low pressure turbine and enters the condenser, okay, where heat is removed and until it becomes saturated liquid. So it exits the condenser as saturated liquid before re-entering the pump. Okay, so at the condenser here will be the heat remove, okay, Q out. At the pump we have the work input. Okay, then we can label the states. So entering the pump, okay, let me use a different color here. So entering the pump will be state 1. Okay, exiting the pump, entering the boiler will be state 2. Exiting the boiler, entering the high pressure turbine will be state 3. Exiting the high pressure turbine, re-entering the boiler will be state 4. Exiting the boiler, entering the low pressure turbine will be state 5. And finally, exiting the low pressure turbine, entering the condenser will be state 6. Okay, so it is key to know that for state 1, the pressure for state 1 and also the pressure for state 6 are the same. The pressure for state 2 and also the pressure for state 3 are the same. And the pressure for state 4, okay, and state 5 are the same. Okay, so based on the values in the question, okay, so the lowest pressure, which is at state 1 and state 6, the lowest pressure is 10 kilopascal. Okay, the highest pressure at state 2 and state 3 is 12.5 megapascal. Okay. And finally, the intermediate pressure, okay, at the state 4 and state 5 is 2 megapascal. Okay, so it is important for us to identify, okay, the pressure at each state. So next we can write the equation. Okay, so let me use the red color here. So for step 2, so based on the question, okay, so number 1, we know we have to find the isentropic efficiency for the low pressure turbine. So isentropic efficiency for the low pressure turbine, LPT. Okay, so we know the turbine isentropic efficiency is the actual work output over the ideal work output. Okay, so we can expand this equation. So taking into consideration the states involved. So for the low pressure turbine, it's state 5 and state 6. So we can write the equation, okay, as actual m dot, okay, h5 minus h6a over m dot multiply with h5 minus h6s. So we can cancel out the m dot, okay, and we can find the isentropic efficiency by substituting the values for enthalpy at state 5, the actual enthalpy at state 6, and also the ideal enthalpy at state 6. So this is number 1. Number 2 is to find the work net. Okay. So work net here is equals to the total work output, since there are 2 turbines, okay, minus the work input at the pump. Okay, so we can write individually the equations. Okay, so we can write individually the equations here. So for work out total, okay, is equals to the work out at the high pressure turbine plus the work out at the low pressure turbine. Okay, so we can expand it some more. Okay, we can write for the work out at the high pressure turbine. So this is when we refer to the schematic diagram, for the high pressure turbine, it's in between state 3 and state 4. For the low pressure turbine, it's state 5 and state 6. Okay, so we can write the equation. So for high pressure turbine, it is m dot h3 minus h4a. Okay, since there is an isentropic efficiency at the high pressure turbine, so the specific enthalpy at state 4 has to be the actual specific enthalpy. For the low pressure turbine, okay, so we have here the mass flow rate multiply with the enthalpy at state 5 minus the actual enthalpy at state 6. Okay, so that is for the work output. So we can calculate the high pressure turbine, low pressure turbine, we can add it up to get the work total. For work in, okay, so work in here is equals to the mass flow rate multiply with the actual enthalpy, specific enthalpy at state 2 minus the enthalpy at state 1, because there is also an isentropic efficiency at state 2. Okay, so we have to find the actual specific enthalpy at state 2. So this is for number 2, and finally number 3. Okay, so number 3, we have to find the thermal efficiency. So we can write the equation for thermal efficiency. So it's equals to the work net total over the Q in total. Okay, or we can use lowercase letters. So work net over Q in total. Okay, so for work net we have calculated. Okay, work net. So we haven't calculated for the Q in. Okay, so for Q in, okay, same as work net just now. Okay, if we want to calculate in capital letters, since there are 2 times, heat is added twice. So we have the Q in primary and also the Q in for the reheating process. Okay, so we can write it individually. Okay, so for Q in primary, okay, referring back to the schematic diagram. Okay, so the schematic diagram will tell us which states are involved. So for the primary, it's state 3 and state 2. For the reheat, it's state 4 and state 5. Okay, so when we write the equation, so for primary, it's m dot, okay, H3 minus H2A. For reheat, okay, is equals to the mass flow rate H5 minus H4A. Okay, so we can add this, add both of these up to get the Q in total, and then we can calculate for the thermal efficiency. So this are steps, is step 2 for the question. So for the next step, step 3. Okay, for step 3, I will continue step 3 in another video. Okay, so okay, I will continue with step 3 in another video. So thank you.